Hey there, guys. Today we are going to start talking about free body diagrams. That's a weird name, isn't it? Like, why are they free? Are they not, has someone got them trapped somewhere? Um, Here is the deal. This is one of the most basic things that you have to learn about and be ready to do in physics. Um, it's just an essential little tool almost um, to be able to figure things out. So as you go into high school and some of you into college physics, I mean, this is just going to be something you do all the time to help you figure out some of those problems. So we're going to practice them a lot. So it's a special kind of diagram. And there's an example of one right here on the screen. And I'm going to walk you through how to make one, how to use them. Then you are going to practice using them until you are sick of them. And then you hopefully are going to be to the point where you can actually create your own physics problem and then draw your own free body diagram. Okay. All right. So we have talked about forces, and that forces are pushes and pulls that provide energy on other objects. Well, a lot of times we want to be able to figure out the motion of an object. We want to be able to predict the motion of an object or describe or explain the motion of an object. And so to do that, we use these free body diagrams. I love them. Here's why. Number one, I get to draw a box to represent whatever object I'm talking about. And I do not draw well. So if I can draw a box and be done, I am pretty happy. So a free body diagram shows the size and direction of all the forces acting on one object in a system. Now, you notice up there I put on and one in red letters because that is such a simple thing for kids to not really listen to, but it will come back to bite you if you don't listen carefully. When we are drawing these free body diagrams, we only draw one object. So we may have a lot of things going on. You could have a horse attached to a rope, pulling a sled with a guy pushing from behind, whatever. We pick one thing. We pick one thing, and we are only drawing the forces that are acting on the object. We are not drawing the forces that the object is exerting on other things. Let me say that again. We are drawing one object, and we are only showing the forces that are acting on the object. And what we do is we represent our forces with vectors. And this is why those, remember I said the length of that vector is important because it's indicating magnitude. And now you can see where we have to use these vectors because we need to indicate direction. So this is kind of an example of what we're moving to, okay? All right, well, if we are going to draw all these forces, then we need to kind of have an idea of the most common forces. Now, there's a few forces that aren't as commonly used in middle school. You'll probably use them more in high school physics, but let's kind of make sure we're comfortable with the main ones. All right, most kids come to 8th grade, and if I ask them to name a force, they're going to say gravity. And a lot of times kids will say, well, gravity is what holds me down. Well, it's really not so much down as it is towards the center of an object that has mass. So here on the Earth, we experience the force of gravity, and we say, yes, that it's directed downward, and that's okay, towards the center of the Earth. So that's a pretty basic one. You know, if I'm going to draw a vector to represent gravity on an object, I'm just going to draw the vector in what we would call down. This is another type of force. Now, this is called the normal force. And again, when I click on these guys and try to use this program, the videos come out kind of weird. So I will ask you to watch this little video. This is called the normal force. Now, the word normal here doesn't mean like regular or, not weird. The word normal here is referring to being perpendicular. And let me explain what that means. So I want you to watch this little video clip first, and then the notes will hopefully make a little bit more sense to you, right? Here's the deal. Anytime we have an object, so let's say here's my box and it's sitting on this table. So I know that gravity, right, is pulling this direction down. Well, it turns out that any time that I have two objects in contact with each other like this, that I also have another force called the normal force, and it's this vector right here. And what it's doing is it's actually supporting. The normal force is that support force that supports the weight of an object on a surface. So if this box is sitting on the table, I know that gravity is acting on this box, right? But this table and this box are also touching each other. So that means this table is also putting a force on that box, and it's putting a nice force on that box to help support it. Because think about it, guys, if that normal force wasn't there, then, and the only force acting on that box was gravity, then the box should be going like boom, like, I don't know, through the table and down, and it's not doing that because it's being supported, right? So the normal force here is from the table pushing up on the box, and it exerts enough to prevent solid objects from passing through each other. So I really like this a lot. Now, here's why it's called normal, right? It's all weird. Because it's perpendicular to the surfaces in contact. All right, don't stress out. Here's the surfaces in contact. I wonder if I could grab, I'm not good with my little pen. Oh, I knew I wouldn't do this well. So pretend that's a straight line. There's my table, right? There's the box and the table. They're touching right there. And the word perpendicular just means that it's making a 90-degree angle with these surfaces right here. And that's why it's called the normal force, okay? Now watch, I bet that stays. I feel like last time that stayed and I had to go and erase it. So let's see if it works this time. Maybe I'm getting a little better. All right, so that's kind of an unusual force. That may be new for a lot of you. All right, I bet this is a force that you've heard of before. This is friction. And if you're not sure what friction is, just take your hands right now and start rubbing them together. Friction is just the force exerted by a surface as an object moves across it. So if you rub your hands together, your two hands are exerting friction against each other, and you'll actually start to maybe have your hands warm up a little bit. Almost always, guys, friction for us is going to be opposite the direction of the motion of an object. There are some exceptions to that. We tend to not use those too much in middle school. So for right now, we're just going to say, all right, friction is usually going opposite the motion of an object. All right, now this one, don't make it hard. It says applied force. All right, that's not a big deal. That just means it's a force that one object applies to another object. So it's applied to an object by a person or another object. So if you walk up to your little brother or sister, if you have one, and shove them, don't do that. You just applied a force, right? You applied a force. You pushed or you pulled on that other person. So applied force is exactly that. It's just a force that is applied to an object by a person or another object. So it can be a push or a pull, right? You could go up and pull your little brother or sister. Don't do that either. The next force is called a tension force. And again, here's a little video clip that you can watch. And you notice that we've got some kids here and they're holding a rope. Well, when you hold a rope or a cable or something like that, You can pull on it, right? You can pull on it. And when you pull on it, that's a force called a tension force. It's just a special kind of force called a tension force. So that's a force that is transmitted through a string, a rope, a cable, a wire. This is always a pulling force, right? Because you're going to pull on these things when you want it to become tight, when you want the rope or the string to be tight. To do that, you'd have to pull on it. So it's called a tension force, but you are still you're exerting a force on those objects. There is a special type of frictional force that acts when an object goes through the air. So it is still friction because as you are, let's say these skydivers are falling through the air. Air is something that sometimes middle school kids still get confused about because sometimes they'll say, well, there's nothing there, it's invisible. Well, it's a gas, it is there. It is actually a mixture of gases, one of which is oxygen, but it also has nitrogen and argon and some other things in there. But trust me, it's a thing. And so if these skydivers are falling through the air, there's actually friction created between their body and the air as they fall. So instead of just saying friction, we give it a fancy name because we're falling through the air. We say it's air resistance. Now, if we get into our physics problems and it says ignore air resistance, then that means trust us. We're just saying, yeah, we know it's there, but don't worry about it. Okay, so sometimes you'll see that in a problem. Oh my gosh, I just saw this recently and put it in there. I literally just saw this like last week. It is the cutest thing. It's these little twins, and maybe this is going to be like they're a little Halloween costume or something. I don't know, but they're dressed as Slinky Dog. Anyway, you can press that and watch these two little twins going around. All right, this is a force called a spring force. Get it? Spring, right here, spring force. And this is exerted by either a compressed, which means to smush together, or stretchy spring on another object. So if you press this, you're going to see some spring forces in action between these two little twins here. They're cute. I hope this is okay for me to use. It was available on, the internet, so I went and got it. All right, now don't freak out. Don't freak out. It's okay. I'm going to help you. All right. Here's how we are going to draw our free body diagrams. All right. So the first thing is we are going to have a little scenario that we read. And then the first thing is we have to figure out the forces acting on the object. All right. And we've kind of got our list over there. We've got our gravity and our normal force. So we'll figure out the forces. We need to figure out the direction of the forces, right? We're going to draw a box, Miss Bug's favorite part, because I don't draw well. So draw a box to represent the object. And then I'm going to draw each force as an arrow coming from the box. Now, I'm going to be honest, guys, those arrows, there is kind of a set way to draw them. We see them drawn a couple of different ways. So here's what I always tell kids. Follow the direction of the arrow. Look, I'm clapping. Can you hear me? Follow the direction of the arrow. Follow the direction of the arrow. And then we're going to label each force. And what we do is we put a capital F for the word force, and then we abbreviate for the type of force. So I might put F and then a smaller G. You guys know I have to get up there. There it is. Now you can see it. And that G is for gravity. Or sometimes I'll see people put a capital F and then they'll write lowercase GRAV for gravity. We might put capital F, lowercase a for applied. I tend to put lowercase APP for applied. I think it's kind of just whatever a lot of your teachers were comfortable with, or maybe what our teachers used when they taught us. Okay, so that's kind of how we label them. All right. So what I want you to do in your scientist notebook is we're going to walk through a whole bunch of examples. And so you're going to write the scenario down. And what I'd love for you to do, after the first couple is I would like for you to try it on your own. And then you can, start the video again and see if you got right. These take practice. Like riding a bike. And the more that you do, you'll get better at them. Or like learning to cook, or like learning to write, or learning a computer, or learning to play a video game. All right, here we go. All right, a skydiver is descending, that means falling, with a constant velocity. And we are supposed to consider air resistance. Ah! Okay, we're okay. Everybody breathe. All right, now, let me see. I know that I would draw a box. Okay, I'll just go ahead. I'm going to do it over here. Don't laugh. I'm going to draw my box. Okay. All right. Now I'm breathing here. I know that I have gravity. So gravity is acting down. Right? Gravity is acting down. Okay. Now it says consider air resistance. Well, I know as he is falling down through the air resistance is pushing up. The air resistance is pushing up. But I'm not sure, here's my vector for gravity. I don't know how long to make my vector for air resistance. So I'm going to come back over here. This skydiver is falling with, and this is important right here, a constant velocity, a constant speed, not speeding up, not slowing down, not changing direction. His speed is constant. If his speed is constant, then he must have balanced forces acting on him. If his speed is constant, he has to have balanced forces, because if he had unbalanced forces and there was a net force, then I would see him speeding up or slowing down or changing direction, and he's not. So that tells me that the air resistance vector should be the same length as the gravity vector. And here, I'm going to put air. Okay, there we go. That's what I think the free body diagram should look like. All right, so I've got it on the next slide. Let me go. I feel like, and I could be wrong, guys, I feel like when I did this before that if I didn't erase it, that it kept the drawing up there. So here we go. All right, let's see if I'm right. Yep. Gravity pulls down on the skydiver while air resistance pushes up. Oh, look, I put she there. Oh, that makes me proud of myself. Might not have been a guy. Might have been a girl. Might have been me. Woo. All right, here we go. Here's another one. Here's our system. A man drags a sled across loosely packed snow with a rightward acceleration. Now, if I remember correctly, guys, I believe that we are supposed to just consider, I think the sled is what we're doing. So let me see here. I believe it's just the sled. Okay, so let me grab my pen. All right, so here's my box that represents the sled. Okay, I know that I have gravity. And the sled is on a surface, right? It says it's on snow. It's on the ground. It's on surface. There it is. It's on the surface, being supported. It's not falling through. So there's my normal force. Okay. Now, this little weird kid without a face, not a head here. I feel like he needs a head. All right, is pulling this direction, right? Okay. Now, if I remember correctly, guys, I would probably label this as a tension force because it's pulling, right? That's a rope and it's being pulled. I think, if I remember correctly, that the answer is just going to call it an applied force. But I'm okay with that. I mean, so we can put it as an applied force or T for tension force. Either one is okay. And now let me see here. He's going, it says a rightward acceleration. So I might be done there, but even though it's loosely packed snow, I still think there's probably some friction. But I'm going to be careful here. Watch. I'm going to draw a friction. Okay, but I don't want that to be as long as this direction because I know that overall the sled has a net force and that net force must be to the right because it says it's accelerating to the right. So I think it's going to end up something like that. All right, so I think that's where we'll be. And watch me erase all this. Okay, and I'm not going to draw these for every single one. I just wanted to kind of get you started. But I can draw them if you need me to. Oh, look, now he has no face again. Okay. Let's see if I got it right. All right, so here we go. Yeah, I did. Now, I was remembering correctly. I would probably label this tension force, but they called it an applied force. All right, so here we go. We've got a rightward force arrow this way, okay? Friction is going to slow the progress and pull in the opposite direction, but notice that the friction vector is shorter than this one because I've got to have an overall rightward acceleration. This is why, this is where we're building on that idea of balanced and unbalanced forces. So we have an unbalanced force situation here, and that means I have a net force, and that means I'm going to have acceleration. And then there's our gravity and our normal force. Here's our next one. A football is moving upwards towards its peak after having been kicked by the punter. Neglect air resistance. All right, so here's what that means. We're not drawing our free body diagram at the point of contact, okay? We're drawing, it's already in the air. There's our football. It's in the air. It is in the air. Now I want to think about what are the forces acting on that football in the air. And it says neglect or ignore air resistance. Okay. That means we know it's there, but just pretend it's not. Well, I think the only force, there's no rope. I'm supposed to it's up there in the air. I think the only force is gravity, which is good because it's going to come back down to the ground. See if we got it. Yep. All right, just gravity. That's it. It'll come back down to the ground. Problem 4. A car is coasting to the right and slowing down. There it is. It is coasting to the right and slowing down. All right, well, it's coasting to the right but slowing down. My guess is if it's slowing down, eventually going to come to a stop. My guess is that I have an unbalanced situation here because it's slowing down. So I know, remember, I have a change in speed. It's slowing down. I still have gravity down. I have the normal force up because it's been supported by the road. Probably have friction, and then I probably have, the motor, we would say, is creating an applied force this direction. My guess this time is that the friction vector, because it's slowing down, is larger. Let's see if I got it right. Oh, I didn't. Look what happened. The car is Oh, there's no applied force because it's coasting. Silly Miss Buck. Silly Miss Buck. See, this is why, listen, these things take practice. They take so much practice. That's why that word, sneaky of them. That's why the word coasting was in there. Got it. All right, because it's coasting, there's no applied force. So we just have the normal force, gravity, and friction that will slow it down. But it's still an unbalanced force situation. I knew that. And I've got this net force, which is going to cause a change in the acceleration. Good one. Good one. Problem 5. A book is at rest on a tabletop. All right. Well, my guess is that gravity's down, normal force is up, it's at rest, it's not moving. I'm going with that I'm done. Yep. Equal, balanced situation, no net force or zero net force. Oh, an egg is free. Whoa, that's not good. Free falling from a nest in a tree. Ignore air resistance. Happily. Let's see. I believe we are just looking at the egg. Draw a free body diagram just of the egg. And again, if I'm ignoring air resistance, I feel like this is going to be the same as the football. I'm trying to think if there's any other force. I don't see a rope. I'm supposed to ignore air resistance. I'm going to go with gravity. I think it's just gravity. Yep. A rightward force is applied. Oh, yeah. See, use the word applied to help me out. To a book in order to move it across the desk. Okay. Consider frictional forces, neglect air resistance. Oh, well, that'll be fun. All right. Well, I think that I have, I think it's going to be a square for my book. A rightward force is applied. So I think there's going to be an applied force arrow to the right. I think there's going to be a friction force to the left, but I think the applied force is going to be longer than the friction force because it says it's going to the right. And I think I'm going to have gravity and a normal force. Did I do it? Oh, good. Yay. Gravity, normal, applied force, friction to the left. And see how that's not as long? Okay, good deal. I like that. Oh, look, a gymnast is holding onto a bar and is suspended motionless in midair. The bar is supported by 2 ropes that attach to the ceiling. All right, now I'm drawing the free body diagram here. And we know we have gravity pulling down. It says that the gymnast is motionless. All right, so I think we're supposed to be like no movement there. So that helps me. And what I would do is draw a gravity vector down. And then probably I would draw force here, force arrow up, and a force arrow up. And have these, since they're ropes, I think that's going to be tension forces. And what I would do is have this arrow and this arrow add up to equal the gravity arrow. But let's see what we got. Oh, yep, good. Tension, tension, gravity. See how those are shorter, but they kind of, if you add them together, they equal that. So that would be a balanced situation. And so the gymnast isn't moving. A flying squirrel is gliding. No wing flaps from a tree to the ground at constant velocity. Consider air resistance. All right, if I have constant speed, then I have a balanced force situation, and I think I'll have gravity down and air resistance up. And problem 10, a rightward force is applied to a book in order to move it across a desk at constant velocity. Consider frictional forces, neglect air resistance. All right. This is kind of similar to the other one, but not exactly, because the other one said was, our book was zipping across to the right there. It was accelerating to the right. This time it says constant velocity. All right. Gravity down, normal force up. Let's see, a rightward force is applied. So I've got a rightward force to the right of an applied force. Okay. It says consider frictional forces. So this time, if it's moving at a constant speed, I think what they want is the friction force to equal the applied force. I think. Let's see. Yep. All right. applied force, friction, normal, gravity. So the book is going across the desk at a constant speed. So it is a balanced force situation. Okay. These take practice, guys. These take practice. And that's what you're going to be doing a lot of. So make sure you have all of this in your notes. And then we have lots and lots and lots of practice for you. Okay, just don't panic. Don't panic. All right, I'm going to panic. Stop sharing. Okay, bye.